So let's start now. This is our 5th lecture, and we are still in vector calculus. So I hope that you, given the amount of time that we are spending on vector calculus itself, you do see the importance and relevance of it within the course. Okay. And today is August 25th. So what we have done till now is we have been talking about fields. We have identified a way in which to represent field, and now what we are into is essentially looking at how to determine some specific features of these fields. And in doing so, till now we have talked about gradient, where phi is a scalar field. We have talked about divergence of a vector field, and the question that divergence tries to answer is how much does the vector field spread out from the point in question. So you are calculating it at a point, and what the operation does is it allows you to get a feel of the spreading out characteristic of the vector field. We looked at another, so this is gradient, this is divergence. And then we have curl. And what the curl does is it tells you about the rotating tendency of the vector field. And while doing all these things, I've also talked about if the divergence is greater than 0, what it means. If it is smaller than 0, what it means. If it is equal to 0, then what kind of characteristic does it predict? And same with curl, the positive and negative, what kind of rotation it is telling you about. I also took some simple examples in order to show that it is not necessary for the vector field to close on itself. It should not necessarily be a solenoidal field. Just that rotating tendency, that is all that the curl operation tries to capture. So this is broadly what I have tried to cover in the last class, and then you went in and you have also done some tutorial problems based on this. So what I plan to do today is try to take this discussion forward via some relevant physical examples, and then conclude this discussion on differential calculus. So that is the plan for today. So let me start today's class by talking about a special kind of field, force field if you wish. These are the central force field. Okay, and by central force field, what I mean is they are directed towards, in fact, let me write it, that these fields are directed towards or away from a fixed center. We have indeed seen some examples that involved central force fields. We did not always necessarily go in and say that these are central forces, things like that. But typically the form that it will take, it's a vector field. So I'm keeping it completely general right now. which I can write in the following form. So you can imagine such kind of fields is that, so there is some center, let it be the center of the universe, and then these fields are either I'm drawing directed towards, it doesn't necessarily have to be that, this fixed center. And the functional form that it takes is it's some function which is in fact the distance of the point from this center, and the direction is the direction along that line. So that's the definition of a central field. And we have seen a lot of examples of this uh, in our school also. So some of the examples that you certainly know are, for instance, gravitation. So for gravitation, this f of r, which is the gravitational constant. We'll be talking about it, and you have all seen it earlier also, electrostatic fields. So for this, not, let me write it completely. Also notice that all of these have this 1 over r square dependence, right? They are quadratic in the distance, and have a feel for what this 1 over r square, 1 over r raised to some power alpha, it looks like. Okay, so have some idea of this, but these are essentially the dependence on the distance is such that beyond a point it's almost negligible. So that's what this dependence is trying to capture. Something else you have also seen, and this is the Hooke's law, if you recall. So the standard problem was you have a mass connected to a spring, and think of it as a one-dimensional problem right now. So wherever this spring is, what it does is it tries to always go towards its equilibrium position. And typically the force you write as, if the horizontal direction is x, so it's a minus kx kind of force. So all these physical forces, fields if you wish, that we often encounter in certain kinds of problems has to do with what we call central force field. Okay. So let us try to calculate the curl of this as having any specific dependence on r. All that we are saying is that it is something that depends on the distance from the central point. So that's the only statement that we are making right now. And what we want to calculate is the curl of this central field. Since we have not talked about different coordinate systems till now, our discussion has mostly concentrated on the Cartesian coordinate system. So we are going to use that coordinate system itself. So this f of r of this field, I'm going to write as, so this part we have already written earlier. Now for the unit vector r, I'm equals y hat plus z hat, and you divide it by the magnitude. So that part, let's just simply write it as r, where this r is the magnitude, the square root of x square plus y square plus z square. Or let me call it some phi r, where this phi r is equal to this function fr divided by the magnitude, where phi r, this is equal to fr divided by r. So once I have written it in this form, and there are other things also that you may notice that it depends only on this radial coordinate. It's not depending on any other coordinate. So that is the idea of this central force field, and that allows for certain kind of symmetry, things that we have not discussed, and hence I'm not raising those points right now. But you can, this is most general, and you can write it in the following way. So then you do your standard thing, the standard way in which one calculates the curl. So this curl I can write it in the determinant form. I'm dropping that r. I don't want to carry it, but you know that phi depends on it. So that's the only thing that you need to know. And z phi. Which you can open and write properly. So this is unit vector x. The second term is minus y hat. And the third term is along the z direction. And now all that you need to do is you need to calculate each of these terms and see what comes out. Two things that you can immediately notice. The first is that in all the derivatives that we have over here, the variable in the numerator, which is z or y or whatever, it does not depend on the variable with respect to which the derivative is being taken. So that is number one. So it will always come out of the derivative. The second is that we know, we would like to know what is the derivative of this function phi with respect to the space variables x, y, and z. And if we calculate it for one, we know what it is going to be for the others. So let's calculate one of them, and the others we can directly write it. So let's say that you want to calculate okay, this was y in the first term. So let's say you want to calculate this derivative. So realize that by chain rule, you can immediately write it as derivative of phi with respect to that variable on which it depends, and then the derivative of the r with respect to y. So now all that I need to know is what is this particular derivative. And I already know what r is, that is square root of x square plus y square plus z square. I don't need to do it in so many lines, but at least once let me do it. And then you take the derivative in the standard way, and what will come out of all this, of this entire exercise, is this r, or x square plus y square plus z square, the square root of that quantity. It will come in the denominator. You will have a half, then you are taking the derivative with respect to y, and in the numerator you will have a y square, so that's 2y. So you can write it as y over r. Okay, and this integral, this derivative that we are calculating, this would be equal to y over r. And as I mentioned, that once you have done it for one, you immediately know what you expect for the others. So if it was the derivative of phi with respect to x, you would get a x over r, the derivative of phi with respect to r. If it was derivative of phi with respect to z, you'll get a z over r. So now we have everything that we needed. So we have all these things. All that we are supposed to do is we go back, we plug it in the right places, and then see what comes out. So if you look at the first term, okay, that is in the x direction, the very first derivative, z comes out, and you have the derivative of phi with respect to y, and we already know what that is going to be. So the curl of this particular kind of field would be given as, so you will have along the x direction, you will have z, the derivative is with respect to y, so zy over r. The second term, similarly, you have the derivative with respect to z, and you have y times phi. So y comes out, and then you have derivative of phi with respect to z. So that will be equal to minus yz over r. Similarly, for the y component, what we will have is the first term is the derivative with respect to x, and then you have z phi. So z comes out. Okay, and the derivative is with respect to x, so you have zx over r, and then the next term. So I'm not going back in the slides. We know what the term is. It's the derivative with respect to z of x phi. So again, that would be equal to x, and then z over r, and then finally the last component, which is along the z direction. And now the first term was, so you're looking at it, the derivative with respect to x of y phi. So y comes out, x over r. And then the last term is the derivative with respect to y, you have x phi. So x phi over r. And immediately you realize that all the terms within the parenthesis or component wise, they cancel out each other. So you immediately observe that equal to 0 along the x direction, plus 0 along the y direction, plus 0 along the z direction, and you can write it as a 0 vector. So what we have obtained via this, something which is intuitive also, is if you have these forces or fields which belong to the category of fields that you call the central fields, and central fields, as I mentioned, they have the property that they are pointing towards. Okay, so that visual picture that I tried to create in the last class, you may use that for your visualization. For such kind of fields, the curl is always going to be 0. So it will not have this rotation property or tendency at all. So that this is a very general result now, right? And all this has come out by trying to understand what these different vector operations, derivatives in a way, that is all that we are doing, because the moment you have the nabla operator and you are operating, it's a derivative, but these derivatives have a specific purpose. The derivatives give you specific information about the nature of the vector field itself. Okay, so that is the first thing that I wanted to say. Now it doesn't stop here, because there are other things also that you can talk about. And there is only one more derivative that you need to take into account, and these are your second derivatives. For those of you who like to do a little bit of thinking, in not necessarily related to the course, think in terms of why the first order and second order derivatives. So there are some very nice things that come out of just thinking about equations and what they can do, rather than taking them to be some mathematical object and you just keep on solving it, right? So just differential equations, if you are thinking the first order versus the second order, what information does it give you, and will higher order derivatives be required? And if you recall, when we were just in this context, when we were just discussing the vectors in themselves, I said that it's the triple product, and beyond that everything can be mapped onto the to a lower level thing. So you can have a cross product of 4 vectors, but you can write it as products, divergence, other kinds of things, but reducing it to 3 operations. Okay, so that is something that is there, and that is why the second beyond the second order derivative, we're not going to think about it. But many other things you can in fact think of by going into these higher order derivatives. So the first one that I intend to take over there, let me go back to my own color. So the first one, so I hope you realize that when I'm talking about second order derivatives, the construction still remains the same. So recall in the first order derivatives, the construction was we had a gradient operating on a scalar. We had this operator operating on a scalar, which we called a gradient. We took the dot product of the operator with a vector. We called it a divergence. We took the cross product of this operator with a vector, and we got a we called it a curl. Now each of these operations, so gradient and curl, gradient of a scalar field and curl, they gave you vectors. So doing those operations, you may get a vector or a scalar. Depending on whether it is a scalar or a vector, you can repeat the operation, right? So if you have a scalar, and you know that you can obtain a scalar via the divergence of a vector field, okay, and once you have a scalar, you can have a gradient on that. I'm not trying to put any physical meaning to it right now, only for the ones that are relevant. I will talk about it. But you see that mathematically this operation is possible. You could also, for instance, you could have a vector. So the gradient of a scalar function, it gives you a vector. And then, since this is a vector, you can do an operation which is allowed to be conducted on a vector itself. For instance, you can take a cross product with this operator itself. You could have taken a dot product, because dot product also works on a vector, and the outcome will be a scalar or a vector depending on the kind of operation that you are doing. You can have a vector which you obtain via curl, and this is the operation that I'm going to start with. You can calculate the divergence of that, or you could have calculated the curl. So remember that these are all permissible mathematically also, and many of them they have a physical meaning also, and that is why you tend to use it in many kind of physical systems. Also, while I'm at it, think about the operations that are not going to be possible. For example, if I asked you to take the gradient of a curl, So you immediately know that the curl is going to give you a vector, and then gradient of a vector has no meaning to it. So this kind of operation is not going to be possible in any way. So I hope you understand where all these are going. The thing that I am not motivating, and there's no requirement for that, is what is the need for a second order derivative. Okay, but that if you are the ones who like to play around with these little mathematical objects that one encounters, think in terms of simple derivatives. What a first order derivative gives you, what a second order derivative gives you. Okay, and you've done these things very early on, right? So you take a first order derivative of a function, you set it equal to 0, you get something, you take the second order derivative at those points, it gives you some other information. Try to construct it from there. You'll see that there's a reason why you do it like this. Anyway, let me come back to what I want to discuss. So let's say that you calculate the curl of a vector field. And remember that even though I'm taking different kinds of examples, most generally you can write this vector field A as something in the X plus something. Let me just remove this part now. I'll come back to all these others as we go along. Plus AY, which could depend on XYZ in the Y direction, plus AZ in the Z direction. So this basically captures all the example that we have been doing. So for the rotation, we did minus Y in the X direction and plus X in the Y direction. That gives you this circulation. For the ones which are like the central fields, we did a X hat plus Y hat. You can make it three-dimensional also. We also took even simpler examples than that. And these AX, AY, AZ could be anything. It doesn't necessarily have to be a linear function or depending only on the X coordinate. These are just in the X direction, what is the value of that function. So if you just take a projection on a certain direction, what do you get? So it could be anything. And the vector field that results because of the way these variations are, it could have all these properties inbuilt into it, right? It could be rotating, it could be diverging at the same time. All these things could be. So there would be curling, but at the same time it's moving out also, right? All these possibilities are there. So when I calculate the curl, so now this time I'm no longer going to write the determinant and write it. So this would be derivative with respect to y minus the derivative of ay with respect to z, the derivative of z with respect to x minus the derivative of the x component with respect to z, the derivative of the y with respect to x minus the derivative of the x with respect to y. And now the second operation that you do is the divergence of this curve. So we know how the divergence operates. You just take the components and you keep on multiplying it. So the x component of the nabla operator, you multiply it with the x component of the curl operation. So again, I'm going to write it directly. It's quite straightforward. So you'll get the second derivative I'm directly writing it over here. I hope that this is clear. If it is not, just stop me and I'll tell you what I'm doing. Okay. So even though one has to write a little bit, but we know what is going on. And again, what you can immediately observe is, for instance, the first term, it's going to cancel out with the third term. They are both the same. Then the second term, so let's put a straight line under it. That has a negative sign, and that cancels out with the fifth term. Okay. And finally, the fourth term cancels out with the last term. And what you get is simply a scalar, which is 0. So fine. So what we have is, if you looked at if you calculated the curl of this arbitrary vector field, and then we took the divergence of it, we got 0. So that is fine. But what is it that we learn via this operation? And in fact, it's hidden in the statement that I just made. When you do this curl operation, so remember that the vector field here has no specific form. It is completely general, completely arbitrary. It could be anything. So the curl operation, what it does is it only gives you the circulating part. So mathematically, when you are doing a curl operation, it only tells you, or it extracts information about the circulatory behavior. And any kind of spreading out behavior, even if it was present in the original vector field, once you've done the curl operation, it's no longer present in that. And that is why when you look at the divergence, since there's no diverging component, there's no spreading out behavior, that is going to be 0. So curl extracts, you can also say necessarily extracts, only the, I'm going to use the word curling again, behavior of the vector field. So I hope that this picture is becoming clear to everybody, that what do you get via these operations. And right now we are not talking about the vector field being an electrostatic field or anything else. It's a completely abstract object as far as we are concerned. It's a field. That's all that we are worried about. And these operations hence are completely general, and the interpretation also is going to be completely general. So the scope of the application is not just limited to a course in electromagnetic theory. So that's the other thing that I would like to impress upon you. Where you may encounter it, when it would be useful, these are all very, to me, these are very relative and abstract concepts in themselves. So I never try to get into them. But depending on what you are doing, it may or may not be useful. But always remember this, that their scope is much beyond what we try to discuss in a course. All right. So moving forward. So this was the first second derivative that I tried to look at. The second that I would pick up, and I'm going to spend a little bit of time on this also. So what if you took the curl of a gradient? Okay, phi is a scalar field. So phi, if you want, we can write as some function of x, y, and z. So I know that gradient, this is something that we have done multiple times now. And now you want to take the curl of this. So again, up to you. whichever way you want to do it. You can in fact write it in determinant form. Maybe that is simple and you can do it in that way. Maybe let's do that, even though that just takes additional time, but writing it directly might be a little confusing also. So what we will have is along the x minus 5 along the y, the second derivative of 5 with respect to x and z. Okay. And one again, I'm not. Our intention is not to be to bring in the absolute rigor at this point of time. So we will assume that we can interchange the order of the derivative without arguing why we can do that or where we can do that. But in most of the cases, we can do that, and that is what we are going to assume at this point of time. And finally, the z component. And again, you see that component-wise, each of the terms, they are cancelling out each other. So curl of the gradient of a scalar function is again component-wise 0 or a 0 vector. So I would like to make at least a couple of observations over here. Maybe you see it, maybe you don't, but let's just discuss it a little bit. So remember what we are trying to do. We took the gradient of a scalar function, and when I was talking about gradients, I have already discussed how you may want to think about gradient. And one of the ways in which you can think about gradients was in terms of those contours, the level curves, and the gradient at each point on those level curves, it was normal to that point. So you will have some kind of contour, and at each point, when you calculate the gradient, it gives you the normal to that particular point. And you will have all these level sets over there. So since as soon as you calculate the gradient of a scalar function, you invariably get a vector field which has this pointing outward or inward, depending on how the values are, but the spreading out kind of thing. And if you try to take the curl of such a behavior, the curl is going to be 0 because it does not have any curling feature or the rotation part associated. So that's number one. That's something that I had discussed when I was talking about gradients and how you may want to think about gradients and things like that. But also remember that I started today's class by talking about these fields, which are the central force field. And there, what we had shown was if you take the curl of these fields, they are 0. And right now, what we have just stated or shown is the curl of a gradient of a scalar function. That is 0. So one can, because these we are completely thinking in abstract, we are making things to be completely general. So from these two, you can make the observation that this field that I am writing, or the central force field, if you wish, that is proportional to the gradient of a scalar field in itself. And without loss of any generality, you can argue at this point that you can write it to be equal to some proportionality constant, the gradient of a scalar. And this proportionality constant has to do with whether you want to take it to be of positive sign or whether you want to take it as negative sign. So essentially what you, or you want it to have negative sign, not take it. And I'll come back to that in a moment. But what one is trying to state or make an observation over here is that if the force field is what you call a central field, okay, then it can always be written as the gradient of a scalar function. Okay. This is always going to be true. You can express it via this relationship where beta could be +1 or it could be -1 also. Typically, in all the examples in physics, the value of beta that you take, that is -1. It's not positive. Okay. And why this is hidden in the idea of the way we think about conservation of energy itself. So let me just point that out to you. So think of a one-dimensional problem. Okay. So something falling under the action of gravity. So we are thinking about gravity, that's the central force, we know that. So let's say, let's take this example. Okay. So mass falling under the action of gravity. Okay. So since I'm taking it to be just a one-dimensional thing, so you can imagine that I can write the Nabla operator in only one direction. So let's take that direction to be your z direction. Okay. And the force field here is simply the gravity field that we are looking at. So I can write from Newton's second equation, mass times the velocity, or acceleration, I'm sorry, acceleration. And this velocity is along the z direction. That I can write using the dependence of the force. So the previous thing that we had just written over here, using the dependence on the force on the scalar field as equal to some beta d phi dz, and this v is along the z direction. So I don't necessarily need to carry on this vector notation with it. Okay. So I'm just let's remove it from here. So v, if you wish, is along the z direction. From just to put it in a form so that my argument is more clear, what I'm going to do is I'm going to multiply the entire equation, the left hand side and the right hand side, with the velocity. So multiplying by velocity, I get mv dv over dt beta b d phi dz. Also remember that the velocity v is the rate of change in the z direction with respect to time. So this I can write it as dt d phi dz, which is equal to, using the chain rule, d phi dt, the rate of change of this scalar field with respect to time. So now I can combine everything together, and I'll have, so I'm going to skip a step over here, but I hope that you realize that v dv by dt, that you can write as half the derivative of v square with respect to time. So I'm going to use that. So m over 2 derivative with respect to time of v square. I'm going to bring the other term to the left hand side, minus beta derivative with respect to time. This is equal to 0. Or derivative with respect to time of this function, which is mv square over 2 minus beta times phi is equal to 0. Okay, and then I can integrate, and integrating, since the right hand side is a 0, the integration of that is going to give you a constant. So finally, what you have after doing all these things for this specific example, and this is general also, minus beta phi is equal to a constant, and now we are going to write E for this constant. Okay, this is a constant. And we have a very familiar form, something that we have seen earlier also. By earlier, I mean in whichever place you have seen some physics ideas, maybe school or elsewhere also. The first term on the left-hand side is your standard expression for kinetic energy. The term on the right-hand side, this constant, is in fact the total energy. And we know very well for this kind of system, because there is no other source of energy that is there. It's the kinetic energy and the potential energy. You look at a combination of that, and that gives you the total energy of the system. So now from here, you may want to think about this constant beta, whether it is positive or negative, what kind of implication will it have? So let's say that I'm just talking about positive and negative. Numeric values don't mean much. Whether it's a +2 or a +10, it's not going to mean much in the kind of discussions that I'm trying to have. So if beta, it is less than 0. So what happens is that you have kinetic energy, and then the second term, which comes with a negative sign over here, that in fact becomes positive, and that is equal to the total energy. And what this essentially tells you about the system, and this is how almost all physical systems that we know of behave, is as the kinetic energy increases, the potential energy goes down. Right? This is also true. It is also true in the example that we have taken, that initially when you drop the ball from some height, all that it had was potential energy. This potential energy kept on going down, and the kinetic energy kept on increasing. You are looking at the oscillations of a pendulum. That's the same thing that is happening, right? Where the velocity becomes 0, it has the maximum potential energy, and then where the velocity is the highest, it has the lowest potential energy. Same in the spring mass problem, where you disturb the mass a little bit, and all these are, since you have written it in this form, your claim is that it's a conservative system. So let's not lose sight of this fact. And having this beta constant to be less than 0, it basically tells you that as one goes down, the other increases. On the other hand, if you had taken this constant beta to be larger than 0, then you're stuck with a system where the difference of the kinetic and the potential energy, that remains constant at all times, for instance. So what would happen in this system is that as the kinetic energy is increasing, the potential energy also has to increase to balance out and maintain the right-hand side at the same value always. You don't have such kind of physical systems. So even though And this is what I'm trying to point out to you. Mathematically, what you obtain is that if the field is a central field, okay, like the physical system that we consider, we call it to be a force field. For that, most generally, it is true that it is going to be proportional, or you can write it as the gradient of a scalar function. In physical systems, the scalar function will have to do with what you call as a potential. And all these things we will talk about in detail when the time comes. But at least this much, I don't think it's very difficult to understand. And it could be anything. They are just related. But the physical systems, they dictate that you always write it as the negative of the gradient of a potential. So I hope that this point is clear to everybody. So what we have tried to establish is that we can always write, for whenever we have such kind of vector fields, we can always write them as the gradient of a scalar function. But when we are thinking of it in the context of what I call physical systems, or where you have these well-built laws, if you wish, through which the system operates, it's the negative sign that you always consider. So I hope this idea is clear to you. I'm just talking to myself at this point of time, but I do believe that maybe you know, but some of these thinking are usually not pointed out when we get into the details of the mathematical derivations and things like that. Okay. So what we have shown, our point was you take the curl of a gradient of a scalar potential, that is 0, and from there, since we already showed that the curl of a force field which is of a specific kind, that is also 0, and then we got to this point. So the central force field and things like that we talked about. What we have also shown, let me see my numbering just a second. 2. Okay. So what we have also shown is that the divergence of the curl of a vector field is equal to 0. This is something that we have already proved. I can imagine this curl of a vector field to give me a vector field, and I'm going to, because it's a vector that will come out. So that particular vector field, let me write it as some field B, where this vector field will have this specific property that it is completely solenoidal, and the divergence of that particular, understandably, it is going to be 0. So again, from here, we can argue in a very similar way that if the vector field is of the other type that is possible, so the first type was this central force field that we talked about, and the second one is going to be this solenoidal field, then you could write these vector fields as the curl of a field which has a similar name as the one in the previous case. Now the difference is that it's no longer a gradient of a scalar function phi, where I said that phi is a scalar potential. This A, and that comes much later in the course, is what you call to be a vector potential. So for such kind of fields, you can look at them also as the curling part of some kind of vector or some kind of potential, which is a vector potential. So this is just on the side. I just wanted to point this out to you. Okay, so two relations I have talked about. I have talked about the divergence of a curl of a vector field. I have talked about the curl of the gradient of a vector field. Let me talk about another one. So this is the third one. So remember, I'm just following that whole thing, that the operations, depending on whether they can be done on a scalar or a vector, I'm just going ahead and doing it. So gradient, this was the last thing that we had talked about, of a scalar field. It gives you a vector. We've already talked about the curl of this vector. So now let's just look at what the divergence of this vector is going to be. And this would be equal to again, just the component-wise operation we are going to conduct. So this is equal to the second derivative of phi with respect to x, second derivative of phi with respect to y, and second derivative of phi with respect to z. This is usually, or this is typically written as on a scalar, where this operator that I have written, it's a second order operator now, where this operator you can write as partial with second order with respect to x, second order partial with respect to y, and second order partial with respect to z. And that is operating in this case. We have talked about it in the following way, but this is a scalar operator. That is something unlike the nabla operator, which was a vector operator. This is a scalar operator, and this is called a Laplacian. Okay. Since this is a scalar operator, it can also act on a vector in which the outcome is going to be a vector. So you could also have the Laplacian acting on a vector itself. Then curl of a vector field is a vector. We have taken the divergence of that already. So now let's talk about the curl of this vector field. This is another vector identity. I think it is also a part of the tutorial, and this is something that is very handy. Okay, maybe after this, if time permits, I'll talk a little bit about the previous thing that I have done. So if you recall, when we talked about the triple product of vectors, I said remember this BAC minus CAB, which is B A dot C minus C, the dot product of A and B. So where are you going to use this vector identity? Using this, you immediately see that it is gradient of the divergence of the vector field minus, now realize that both A and B in this, they are the nabla operators. So you have the divergence or the dot product of the operator with itself, and it should operate on something to have any meaning. Otherwise, these operators, they have no meaning. So what you will get is your Laplacian. So this is one place where the Laplacian comes naturally, operating on a vector field. And that's why I said it's a scalar operator. It can also operate on a vector field. So One thing again that you can immediately notice just from the way it has been written, that took the curl of a curl of something, and that you are able to represent in terms of two independent vectors. These two independent vectors have to do with the gradient of a divergence of a vector field and then a second order derivative. Where this comes in very handy, or where you will need it, this is the identity that you require when you try to get the wave equation from Maxwell's equation. Okay. Again, I will say that you may want to think about these second order derivatives a little bit. It would make sense. But these are some of the important ones that you will need, that would come out to be useful. Where, let me go back to the previous one for a moment, where this Laplacian operator becomes useful. And rather, let me put it in this way, where these different kinds of things that we are trying to just put it in front of all of us, where it becomes useful is that the objective is to get a description of the field. All these are essentially giving you one method or another method which allows you to reach that description. And the reason that you need so many ways in which you can want to think of the problem and try and look at it, it's because not always the setup of the problem will allow you to use only a single formalism, or that might be the simplest one to use. So it's not only about solving a problem, it's also about solving the problem in the easiest possible way and trying to solve different kinds of configurations. For instance, where this formalism becomes very important is if you think of simple case, two capacitor plates, parallel plate capacitors, something that we have seen, we know, okay, this is grounded, and you have some charge distribution that is given, and you want to know what is the field between these two plates and how it varies. One of the ways in which you can think about it, because remember these second order derivatives, they are giving you the variation in space. Okay, so you can try to look from that point of view, and since you know the value of the potential on the two plates, you have the necessary condition satisfied through which you can solve. You had the I am assuming that we know about initial value problems, boundary value problems, and all these things. So since you know the value at the boundaries, you have all the information in order to solve the problem. And once you know one, since you know that the force field is a central force field, you can, from the potential, you can always get to the field and things like that. Okay. So all these are leading to the same thing. The problem will determine which one is more handy. The last one, as I said, this is the most important identity that you use in order to derive the wave equation. And remember, I have not really listed down and said, okay, we start with electrostatics, which is static charges, we allow the charges to move, that gets into magnetostatics, steady currents. Then from there, we talk about Ampere's law, Faraday's law, Maxwell's law, which is the Maxwell's equations, which is the high point of a course like this, because that is in fact the most important thing. And then towards the end, one then talks about different kinds of phenomena that using Maxwell's equations you could explain. And the most important point over there being combining these optics with the whole idea of electromagnetism. Right? So these are your waves that you are thinking of. So all these are inbuilt, and to have a uniform comprehensive description, you need to go through all these things. Okay, I think that basically culminates the differential calculus part. I still need to do the integral calculus and then the different coordinate systems, which may take another 2 to 3 classes. But I hope that you realize why seeing them beforehand at a single place, trying to build up the intuition is something that is required. Okay, so there is still some time, but I don't have time to start with the integral calculus. So I think I'm going to at least stop with me speaking, and if you have questions, I'll take it.